Is that better for the screen? It's kind of washed out otherwise, right? It's not too dark, I don't think.
How many people usually show up to class?
On a good day, we get 12. On a snowy, wintry day like today, 3. Well, good afternoon. I think we're ready to start. Welcome to everyone who's here in person. Welcome to everyone who's here online. If you are online and you are worried that the classroom is too crowded, it's not. So if you feel like you want to come in person, you're more than welcome to. We typically have 10 or fewer show up in a classroom that's big enough to hold over 100. So just know that. For online people, if you could let me know what the audio quality sounds like. If it's good on your end, that's good for me to know as well. Too loud, too quiet, too robotic, any of those sorts of things, I can try to fix it on my side. What else? I sent an email around today, just a reminder of a couple of the deadlines around the unit assignments. I also gave some comments on assignment 1. So I still have probably around 20 more that I have to get through. And so if you are still waiting on a grade, sorry for that, but yeah, I'm actually way ahead of where I expected to be at this point in terms of getting these grades out, because there's many of them. And huge thanks goes out to the TA that is working for me for the course. I also, and some of you may have spotted this, I posted the parameters around assignment number 2. And I've set a due date for assignment number 2 of April 1st, not April Fool's, well, it is April Fool's Day, but it's not an April Fool's Day joke. That is, what is that, 30 days from today? So, hopefully that's plenty of time. And this is an assignment that I've done now every year for a number of years with maybe some minor modifications. What this entails is you, either on your own or in a group of up to 5, creating what I call an educational resource, which is a video. Now I've created, well, this is 12 now, I guess, just for this one course. What I want from you, though, is not an hour-long lecture on some topic. What I want is a quick, short, informative video, because I know that with the exception of this class, people don't like watching huge, long videos on YouTube. So the idea is to make a short video. Not only that, if they're an hour long each, that's way too much time for me to hope to get through them. So I want videos from 2 minutes to 5 minutes. They don't have to be fancily edited or anything like that. But if you do have that skill set, that's certainly welcome. You can do it in groups of up to 5. And maybe what I should do in the next week or so is post a bunch of links to really good ones from the past years. And so you can get an idea of the sort of, maybe the range of what you can shoot for. So this assignment is going to be a video, but if there is some idea that you have that you would rather do than kind of what I posted in that document, and I detail this in the document as well, please just reach out to me. If you have an idea that's going to involve a group size greater than 5, there might be fewer of those this year, just with group limits and COVID making it more difficult to get together in groups. But if you have an idea that's something different, just get in touch with me one-on-one. If it's outside those parameters, usually I let them through if it's reasonable. Of course, with exceptions. So just read that document very closely and carefully, and if you have any questions at all, please reach out to me. I'm trying to get better with email. I know I get lots, and so my problem with email is I'll check it on my phone, and it'll be too awkward to respond on my phone, so I wait, and then I see that it's already read, and I forget to go back to it. If you feel that you're in that situation and you need to get an answer from me that I missed, please don't hesitate to email me a second time. I do not get offended if you send a second email, although I am trying to do my best with those, and yeah, apologies if not. One thing with these videos is just notice at the very end, I've banned a few common video types that people have been doing. So a very popular one in previous years was the Diet Coke and Mentos experiment, where you drop a Mentos into a bottle of Diet Coke and it shoots up, and people will explain the, I guess, the physical chemistry behind what's going on there. It got to the point where like a quarter of the videos that were being spitted were that exact same thing. And so I'm tired of watching them, and I'd like to see expand your not expand, but like just be a little more creative with it, come up with some ideas. And yeah, if you have any questions about whether your topic is allowable or appropriate or whatever, please just let me know. I'll do my best to get back to you. We are starting a new unit today on global warming, as you can kind of see in that little picture on the side if you're online, or on the main screen if you're here. And this is going to be our final unit in the area of gases. Where we had the first unit was on, the common pollutants, SO2, NO2, all those ones. Next one was on ozone and CFCs. This one is on global warming, which is probably the primary environmental issue that's facing us right now. It's not the only one. There's other big ones like plastics in the environment and et cetera, but certainly this is one of the, probably arguably the most important one of all. This is a picture from last winter. This was, well, our winter, their summer. This is the Australian wildfires, which is just one example of one of the consequences of global warming. So I'm going to show you a couple of pictures just to give you an idea of what we're talking about and the scale of what we're talking about when we're discussing global warming. This is a picture of well, taken from the same spot, taken from the same vantage. In Alaska, it's the Moyer Glacier in 1941, and then the same area in 2004. You can still sort of see up here a little bit of the glacier left, but as you can see, in that 63-year span, almost all of it has disappeared and it's left by this great big lake. And this is a story we're seeing all over the world. This is another glacier in Norway, and you can kind of see here the thickness of that glacier, and it's basically gone. It's sort of retreated to like a small little area over there. Huge amounts of glaciers that were once very prominent and large, disappearing on the scale of a lifetime, human lifetime. This is another one in Argentina in 1928 and 2004. And this is especially concerning for places like Argentina and places in South America along the Andes Mountains, because as these glaciers melt, the meltwater, the runoff water, is actually used as drinking water for many people that live in the nearby vicinity. So once these glaciers are like fully gone and there's no more meltwater, there's going to be potentially a big water crisis in these areas for sure. This is one here in Canada, the Athabasca Glacier, and what they do is you can see kind of the edge of the glacier right there. Every year they place a new stone to indicate where the edge of that glacier was, and you can see where the edge was here in 1992. And of course, every stone here is 1 year since along the way. So this is one that you can actually go visit if you've never been to a glacier before. I've been to one before, actually not in Canada. I don't think I've been to one in Canada, but one in Iceland. And in Iceland, you can actually go cave hiking, which I did, where you get the crampons and you can go in with the picks and everything. And there's all these caverns that you can explore. And these caverns are basically the edge of the glacier. It's meltwater. They've melted out and left all these kind of channels that you can go in. And you can see it's like rushing rivers in there of water just constantly melting and coming off the glaciers. So it's very obvious. And the tour guide, when I went, would say that the edge of the glacier where they start their tour every week goes back by like a few dozen feet. So it's like very, very obvious for them. So perhaps the most obvious way is to measure the change in climate is to just look at average global surface temperatures. And these are the values from 1880 to present, where this line here, which is sort of 0, is the average between 1951, which is about here, and 1980, which is about here. So that average is this line here, which was extended forward and extended backwards. And what we can see is the late 1800s, early 1900s. The average global temperature is roughly negative 0.4 degrees Celsius, below that average. But since about 1980, what you see is this big upward increase. Pretty rapid, considering that's 40 years. I was born here, 77. So, yeah. And the change so far has been around 1 degree Celsius. And this is on average over the whole globe. It's not the same everywhere. Some places have actually gone down a little bit. Most places have gone up. Some have gone up quite a bit. Some have gone up just a tiny bit. So this is a way of measuring it over sort of the whole planet. And you can see there's many different studies using slightly different methods, coming up with slightly different results, but they all are quite close to each other, and they're all certainly trending in the same direction. This is a map showing what the anomalies are depending on where you are on the planet. So this is the average over the span 2014-2018. And if it was white, like you can see there's some areas like over here where it's white. White means basically no change from the 1950 to 1980 average. Yellow means a little bit above. Red means quite a bit above. I think the reddest point on this graph is 4 degrees. You can see this 4 degrees Fahrenheit, which is what, 2 point something Celsius. And blue means it's actually cooled down a little bit. And so what we see is that the reddest areas are those areas closest to the North Pole. And those have increased much more than, say, around the equator. Around the equator has warmed a little bit, maybe 1 degree Fahrenheit, which is a fraction of a degree Celsius. But that's offset by extra warming near the pole. You can see actually just kind of offshore from where we are right now in Nova Scotia, a big area of blue. So this is an area of the ocean that's actually experienced some cooling. And this is believed to be, at least in part, due to changing ocean currents and melting of ice in the north and in glaciers and so on running down here. So some areas will cool off as cold water rushes into those areas due to melting in those Arctic areas. So there's nothing special otherwise about that particular area. And you can see it certainly in some places around Antarctica as well, where there's melting going on. Pushing cold water into the area, you get a colder average temperature. Melting ice caps are certainly another phenomenon that we've been observing and monitoring in Canada pretty well every year. Where this was the white that you can see up top was the extent of the ice cap above Canada, right? Like this is Canada over here. So in the north, around the North Pole, this is the extent of the ice cap in August 2012, where the average, I think it was like the 1980 average, 50s to 80s, was this line here. So what we're seeing is this sort of dramatic contraction of the extent of ice coverage up in the North Pole as well. So in addition to rising temperatures, in addition to disappearance of glaciers. And this is just showing the mean value. I guess this is from 1981 to 2000, would be this gray line here, which is now quickly becoming a red line. That is the extent of sea ice, depending on the time of year, because of course it's going to grow in the winter and shrink in the summer. Between 81 and 2000, and that kind of gray hazy area around it is sort of the noise that you'd expect, the variation within those years. And what you can see is that pretty well every year since, by September, by the time the summer is just ending and we're getting back into the colder season, every year essentially since 2007, it's been lower on average than that average extent we saw over that decade. So what we're seeing is every year it's getting a little bit smaller. consistent with the warming temperatures that we're seeing up there. So this can be a problem, not just for human beings, of course, but for many other organisms that live up there that depend on Arctic sea ice. For example, the polar bear makes use of Arctic sea ice in order to hunt and find seals and so on. And when that gets shrunk, their habitat changes and it forces them to be more on land. And I don't know the exact ecology behind what's been going on lately with polar bear populations, but it's kind of one of the poster animals that you see quite a bit in the discussions of the northern sea ice. So this is just a plot showing the average sea ice, and you see it varies from year to year, up and down with the seasons going back from 1980. It's following this pretty straight blue line downwards, so we could probably predict going forward what the fate of this is going to be. An interesting thing that I wanted to point out that you'll often see by looking at this long range of data from 1980 to, I guess that goes to 2017, it's pretty obvious what the trend is, right? It's this blue line, it's decreasing, it's decreasing, it's decreasing. What you see every time you go from a year like 2000, whatever that is, 6, I guess, up to 2008, notice that that's a big increase in that 2-year span. Is a lot of people will look at this and say, oh my gosh, the North ice is healing. Global warming is over, or climate change is over, it's not real. Of course, what they're doing is zeroing in on a very small range of data, which is not representative of the overall long-term trend. It's arguably, it's kind of like noise, right? Like it kind of varies up and down. It's not going to perfectly follow that blue line, but the trend certainly is clear when you look on a broad range. Untitled Chapter, and I'm probably not pronouncing that correctly, but this is a location in Greenland where this translates to warming island. It's in Greenland, and you can see it's kind of this area here. It's an island, or probably more correctly, a series of islands that are, I guess, new islands. They're considered new islands. They were unknown before because they were covered completely year-round in sea ice. So it was like covered in a glacier, basically. And it was only since, like this is 1985, this is 2002, it's been only in that year span where this has sort of become exposed. People recognize that there's this new land feature that's under there because it was never visible before. So this is just maybe one of these sort of stark reminders of the extent of what's taking place, especially up north, which is experiencing the greatest amount of warming. You get people like Donald Trump saying this is very expensive, global warming bullshit has got to stop. Our planet is freezing, record low temps, and our global warming scientists are stuck in ice. This was back in 2014, before he was as household of a name as he is now. Of course, he was still a household name then too, but I guess for different reasons. But certainly this has been a feature of the public discourse around the topic of climate change dating back all the way into the 1980s, where people were starting to sort of raise alarms. Scientists were starting to make observations. And remember, I say this all the time, but there's the stages of sort of coming to grips with large-scale environmental problems. There's the recognition of the problem, which is often done by, well, in this case, I guess, climate scientists. Recognition of the problem goes hand in hand with understanding what the source of the problem is, what's causing the problem. Number 2, there's the technological solutions, and number 3, there's the political will. And I guess those are, don't necessarily have to happen in order. They can happen together as well. But this, I guess maybe I should insert a second step in there. There's discovering what the source of the problem is the first step. Maybe the next step is convincing everybody else that this is something we need to be worried about. Because I feel like this is finally the step we're getting past in this issue of global warming. I'll talk about that a little bit more later. So 2014, on the scale of the public discourse on global warming, is actually a long time ago, thankfully. So one thing that we know for sure is that the seas are rising. Sea levels are increasing. This is the level of the sea from early 90s to, I guess, just a couple of years ago. This is in units of millimeters. So of course, 1,000 millimeters is 1 meter. So 90 millimeters is basically the amount that the sea level has risen in the last, I don't know, 25 years, which is a very, very short period of time on a historical scale, or certainly a geological scale. It's like a blink of an eye. And certainly we can predict again what the trend is going to be going forward if nothing changes. So sea level rise is obviously a problem for lots of different reasons. This is actually a picture showing the high tide level in 1998 versus the high tide level in 1743 in Louisbourg, Nova Scotia, up on the northern, like close to Sydney, right? You can kind of get a sense of the scale here because there's a person standing there, assuming he or she is, I don't know, 5'8". You can see that this is at least several feet in difference. I will say this though, that difference that you see from 1743 to 1998 is only partially a result of sea level rise. The rest of it actually, and this is true in Nova Scotia, is the result of the actual continent, the continent settling down a little bit. So you could say, I guess Nova Scotia is sinking just as the sea level is rising. So we've got a bit of a double whammy here. There's other places that are rising. If you're on the west coast, there are certain places that the sea level is certainly rising there, but the land is actually coming up as well due to geological changes. So we have a new set of questions for these as well. I hope these are open for you. I set them to time to be open as soon as this class started. So yeah, I'm getting some nods, so that's a good thing. Where have the greatest temperature increases due to global warming been? That sounds like bad. Where have increases been located? It's a little awkward, but hopefully you understand what I mean. Where has the temperature increased the most? And if you look at the picture, it might help you out a bit. But the answer here is going to be near the North Pole. Is where we're seeing the bulk of the increase temp. Sort of the opposite, right, of the ozone hole that was on the South Pole. So different problems for different places. Question 2, what is significant about Untitled located in Greenland? And the answer here is C. It's a new island recently exposed by melting sheet ice. Please don't answer D. It's where the Paris Climate Agreement was signed. That's why we call it the Paris Agreement, actually, because it was signed in Paris. So why is the sea level rising? There's actually two reasons behind what's going on with the sea level. One is that when you warm up a liquid like water, it will actually increase in volume. Many things, if you heat them up, will increase in volume. That is true for water as long as water is above 3.8 degrees Celsius. If water is colder than 3.8, if it's like +1, warming it up to +2 actually causes it to shrink a little bit. But if you warm it up past 4 degrees and the average, I believe the average surface ocean temperature on Earth is more like 17 degrees Celsius. Warming that water up will cause it to just expand. So that's one thing that's going on, is water is just expanding just as a pure consequence of it absorbing extra heat of it warming up. So yeah, this is The average temperature is 17 degrees. It can vary anywhere from about +2 to +36 degrees Celsius. Probably it'd be closer to the +2 end if you went out and went for a swim right now in the Atlantic, you know, off of Wolfville there. I lived for a while on the West Coast, while Victoria, Vancouver Island is much warmer here in the winter. Like they barely ever go below 0, almost never get snow. The water's actually a lot colder. It's typically, I don't know, somewhere between maybe 4 and 8 degrees Celsius. It's never comfortable to go swimming there without a wetsuit, where at least here, if you're close to the shore, it will warm up. Part of that is because here in Nova Scotia, we have 2 dominant ocean currents. We have the Arctic current coming down, which keeps us cold. We have the Gulf Stream, which is coming up. And they kind of meet around Nova Scotia, so depending on which is dominating, we can have nice water temperatures. The other thing that we have here is a fairly large continental shelf. So the water actually extends out without getting too deep. We're on the West Coast, it kind of plummets down into nothingness very, very quickly. So you don't have to swim very far out before you're in like bulk ocean. But yeah, the average surface temperature is 17 degrees, which it can reach that in certain areas. What we find though is when you go very deep down, you know, this is, if you go down a couple 100 meters for sure, the temperature after the first, say, 300 or 400 starts to drop dramatically from whatever the average is, very close to 8 degrees. So no matter where you go, the ocean is cold when you go down deep enough. So really there's kind of 2 factors, and there's been a lot of work actually been done, people trying to figure out exactly what the relative importance is of the different factors contributing to sea level rise. They know between melting of glacier, like sea ice, and long-term melting of glaciers, and I think the estimate is around 50% for that, and somewhere around 50% for thermal expansion. So they're, I'd say, equal contributors. And a paper just got published this past summer on this topic where they do a lot of modeling and try to figure this out exactly. But really, there's these 2 important factors which are giving rise to this observation. So yeah, we're rising tides. What does this mean for us? This is not a real photograph, right? But you see images like this sometimes in like sci-fi movies that are set in the future, dystopian movies where sea level rises happen. The one that always comes to mind when I think about scenes like this is AI. If you ever saw that movie, it's a really kind of weird movie because the director died like halfway through the movie and they replaced, so who was it? Was it Stanley Kubrick? And then he died, and then it was replaced by Steven Spielberg. And they both had very different styles. So it kind of starts out and it's very like dystopian and kind of creepy, and then like Spielberg takes over and it becomes like kind of like got a happy ending, and it's like it's got a really weird tone. But anyway, it's set in the far future where sea level has risen to the point where you're submerged, like cities are being submerged. I don't know if that's what we're really worried about in the near term, and even by near term, I mean maybe in the next 100 years. But certainly there are some locations that are already experiencing these effects negatively. This is a place called the Nukuoro Atoll, which looks like it'd be a fascinating place to visit. But what you can see is everywhere that's kind of this kind of tan color is beach. It's kind of sand. And everywhere where you see the darker, that's like vegetation. There's trees and whatever else that are growing there. And you can see there's this kind of connector here. So as the tide comes up and down, water can go in and out of that outlet. It just seems kind of like it'd be a neat place to be able to, I don't know, go swimming in the inner part or kayaking or something along those lines. But anyway, as you can guess, the highest point on this atoll is not that much above sea level. And this type of place would be extremely prone to even minimal sea level rise. National Geographic a couple of years ago forecasted what the landscape of North America, well, the whole world actually, would look like if all of the ice, basically all of the ice that's at the North Pole and on glaciers and so on melted and went into the oceans, and we kind of had a worst case scenario warming situation. And I believe this translated to around a 7-meter rise in ocean levels. And this is what the North America would look like. It's kind of hard to see what's going on there in Nova Scotia because we're kind of small, but certainly if you look in Florida, Florida is actually very low, and almost the entirety of Florida would be underwater in this scenario. You know what the highest mountain is in Florida? It's Mount Everest. And you're probably looking at me like, Mount Everest isn't in Florida, it's in Nepal. Well, there's another Mount Everest in Florida at Animal Kingdom, Disney. It's called, what is it, Expedition Everest. And it's a roller coaster. And yeah, that's the highest mountain if you get to the top of the roller coaster in Florida. The second highest mountain in Florida is Space Mountain. So gives you an idea of what the land is like in Florida. But as you can see, kind of going all the way up the coast, there's all kinds of places that will be underwater, which are currently very densely inhabited. One thing about human beings is we typically like to build our cities and so on where it's close to the sea for shipping and other reasons like that. So there's potentially a lot of people displaced in this scenario. This is another one looking at Asia, and you can see, large parts of China would be submerged. That white line, by the way, is the current boundary. Bangladesh. There's huge numbers of people who would be displaced in a scenario like this. 600 million people in China, 160 million. So yeah. Another feature that we think we're seeing, it's the data is very noisy, so it's hard to maybe say definitively at this point. But there's an expectation that as the Earth increases in temperature, as especially the surface temperatures of oceans increases, we're expecting to see a greater number and severity of things like tropical storms, things like hurricanes and so on. Because what happens is these hurricanes, when they develop and they travel across the ocean, if the ocean water is warm, it accelerates them, and if the ocean water is cold, it decelerates them. So if you increase the temperature of the water, you're expecting to have on average more acceleration, which means more storms, stronger storms, and of course these cause all kinds of damage once they make landfall. So this is something else we get to look forward to, I guess, as a consequence. Golden toad. This is a species of amphibian from Costa Rica, which has gone extinct. And this is believed to be the first actual extinction or confirmed extinction as a result of climate change. And it says here, they made only during a few weeks in April and May. They depend on seasonal pools of rainwater in which to lay their eggs. So their biological cycle is very specialized for their particular microclimate of where they live. If they need a wet season, when they're ready to reproduce. Their range is only like a 5 square kilometer region. So they're extremely prone or extremely susceptible to changes in climate and not super able to quickly relocate. They're not like birds or fish that could quickly potentially find new habitat. So warming surface temperatures in the oceans changed the rainfall cycles and created this issue. And this is being played out all over the world, maybe not as dramatically in terms of full extinctions at this point, but certainly it's something to expect down the road. A couple of years ago, I was in Newfoundland, and I did a tour in Bay Bulls, which is, I think, south of St. John's, where they take you out and it's whale watching. There's islands that are covered in puffins, so you can see puffins, and glaciers if you're there the right time of year. I didn't see, not glaciers, icebergs, which come off at glaciers. I saw the puffins, but I didn't see anything else. But what happens is the puffins all come to this one place at this one time of year to meet up with fish that arrive in the same area. So there's feeding, and there's worry that if ocean currents change or so on, a whole population could just get wiped out because they arrive the third week of May in this one area when the fish arrive, and the fish are 3 weeks later, therefore all the birds will starve. Like, this is the type of thing that what might seem like a small effect can have a giant impact on the whole population. What two factors are most responsible for sea level rise? As we discussed, the two things were thermal expansion of the water and melting ice. So it'd be C. Displacement by boats is not it. Although it's probably something, right? If you took all the boats and they pushed the water up just a little bit. I don't know. We don't have that many boats. There is a 7.4. I don't know why it's not on my slide right now, but 7.4, I believe, is a question on the golden toad. We just covered that as well, so I don't know what to tell you about that. Let's move on. Jasmine loves those puffins. Jasmine, you're from Newfoundland, aren't you? So she maybe can confirm my story. I actually have a friend, and she grew up she was like the house next door to the place that rents or sells you tickets to the tour in Bay Bulls. So, yep. Great spot. More doom and gloom. Coral bleaching is another thing. Coral is, well, you know what coral is, but it's made up of colonies of small organisms that secrete these, calcium-based shells. Healthy coral kind of has this darker look. It's constantly growing. It's very important for creating habitat for all kinds of sea life. What has been noticed in the last, I'd say, decade are what we call bleaching events, where the temperature rises in the vicinity of the coral to a degree where it kills the coral organism. And it causes bleaching. They die, it turns white. And coral can't sort of quickly relocate. Like if a fish is in water and the water is a degree warmer than it wants to be, it can just go deeper or swim away. But coral obviously is stationary and cannot relocate in response to temperature changes. Great Barrier Reef health outlook downgraded to very poor due to ocean warming. This is just not last August, I guess. That's 2 Augusts ago. But this is another expected consequence. So hopefully I laid out enough evidence to convince you that this is a real thing that's really happening and is something we need to be concerned about and something we need to act on. And I think, as I mentioned before, the first stage of all of this is understanding what's causing the problem and maybe what we can do to fix it. There's a lot of people who don't believe that this is really happening, although I will say this debate, in quotation marks, this debate is entirely a public thing. It's no debate within the scientific community. Scientific community is really all on board. It's kind of like the anti-vax movement where the medical establishment, the science of medicine is very unanimous on the efficacy and importance of vaccines, and the debate on vaccine safety is completely in the public, in the media, in online chat rooms and YouTube videos and these sorts of things, not within the scientific discourse. So what is causing global warming? This is an old paper now. This is back in 2004 when the final form of it was actually received and published, where a number of climate scientists used data that they had, and they used simulations and they used forecasting to try to look at a number of possible factors that could potentially give rise to global warming. And there's all kinds of things that you'll see people suggest. Obvious one that I'm sure you all have heard before is greenhouse gases, like carbon dioxide. Some people talk about fluctuations in the brightness of the sun or sunspots or a number of other possible causes. Some say it's naturally caused by maybe volcanic activity or things like this. Basically, what this paper does is looks at each one of those and tries to see what impact, if any, that could have on the observed increases in temperature that we've seen up to 2004. So it's missing like the last 15 years of data. This is what was observed at that time in terms of temperature fluctuations, which is the black line. They looked at all natural causes, and they see the red line. So the red line, basically if it's along this line, that means no warming or cooling. And looking at anthropogenic sources, meaning man-made or human-made sources of pollution, we get very good agreement between what's actually observed and what's predicted based on their model. Climate scientists, this is actually a very interesting piece of information. A question was asked to many climate scientists and to many members of the American public whether they believe climate change is A, happening, and B, caused by human beings. So if you believe both of those things are not true, that was, in 2013, a substantial fraction of the American public, more than half. People believed that it was either not happening or maybe it's happening, but it's not human beings that are causing the problem. And this is hugely problematic towards trying to fix the problem, because if the public doesn't believe that it's a problem or a problem that we can do anything about, then politicians who get voted by those people have no real motivation to do anything about it. 41% though said yes, so that's I guess a good thing. Climate scientists were much more definitive. 97% were on the yes side here. This is another one this is another poll looking all the way up to 2020. So this one was more recently done. And what we can actually see is that in the US, there's been a big shift in public perception around climate change. Not as big maybe as you might hope. But from November 2019, the answer went from 43% to 63% of Americans who believe that the Earth's temperature has been increasing in the last couple of decades. Okay. Which is good because we're seeing this shift in perception, which I think is necessary for there to be a shift in political priorities around something like this. So global warming, what's causing it? And I said I think we have a very good idea now. And this is a chemistry course, not a climate science course, so why are we talking about this at all? Because it is chemistry, it is chemicals that we are emitting, and it is human behavior, it is chemical phenomena that are responsible for the whole process of climate change. So here's a basic primer. We know the Earth is constantly absorbing energy from the sun. Right? We have this light coming from the sun that's being absorbed by the surface of our planet. We see this in the form of visible light when it's daytime. We know, what is it, around 8% of that is UV. We said, I don't know what it was, 43 or 41%, I don't know what it was, visible. And like the remainder, like 50%, is in the infrared part of the spectrum, which is lower energy. We can't see it with our eyes, but it's certainly coming from the sun. What that does is it causes the sun to warm up, and it actually increases the temperature. Well, it keeps us a very warm planet, warm enough to sustain life. Because we are now a warm planet, what's happening all the time is our planet is also emitting light back out into the solar system. And I'm going to talk about how that happens and why that happens in a second. But what you can see is the Earth, from both the side that's being illuminated, where it's day, and the other side as well, you can see that light is being emitted out with all these arrows. And so the Earth is sort of constantly absorbing energy from the sun and is constantly emitting energy back out in the form of light as well. And these two, once they're balanced, means the Earth will just maintain a constant climate over decades without warming, without cooling, as long as these two are balanced with each other. So what is this? You know, we don't think of the Earth as emitting light all the time, but it actually is. There's something that we know that's a phenomenon in, I guess, physics, we could call it blackbody radiation. And what blackbody radiation is this phenomena where any object will be emitting light all the time, and the amount of light and the color of light that it emits is a function of its temperature. So as the temperature gets higher and higher, the amount of light it emits is greater, and the color becomes on average higher in energy. So this is a map which is showing, I guess, the spectrum. We see the ultraviolet part, we see the visible part, we see the infrared part, and an object at 3000 degrees Kelvin, which is 3000 degrees Celsius above absolute zero, which is like 2700 degrees Celsius, will give off a light spectrum which looks like this. This is going to be a very hot object, by the way. What you can see is the peak amount of light it gives off is somewhere here in the infrared. It's got a question, does that mean humans are technically emitting light? Yes, we are. We're all emitting light right now. The peak is somewhere in the infrared part of the spectrum, and you can see it's emitting some light in that part of the spectrum as well. So it's emitting a little bit of red, less orange, not very much yellow, green, or blue. But it is emitting a bit of red. If you increase the temperature up to 4000 degrees Kelvin, what we notice is the maximum shifts to shorter wavelength, to higher energy, and then the overall size of that peak is bigger. So you're going to get a lot more red, a lot more orange, a lot more yellow, green, and blue. And eventually, if you get it hot enough, if you get it to 6000 degrees Kelvin, you can get it so that the peak is in the visible part of the spectrum. This becomes very bright, and like a light bulb, if you have those, you know, the old incandescent light bulbs with the tungsten filaments, if you get that filament hot enough, it becomes very bright, it gives off a lot of light, and it gives off mostly light in the visible part of the spectrum. And this is actually how we can tell the temperature of faraway objects. This is how we know how hot the sun is. We can look at the energies of light given off by the sun. We can match it to what we would know the light given off by a hot object would be on Earth, and then therefore say, oh, well, we know the sun looks a lot like that, so the sun must be 6000 degrees Kelvin. And we can do that with distant stars as well. But if you have an object that's hot, but not like hot as the sun, it might look just a little bit dim, but red. It might be red hot. Yeah, I'm going to skip that one. So if you have an object that's body temperature, we are giving off light right now. That light is all in the infrared. We're not giving off really any light that's in the visible part of the spectrum. So if we turned off all the lights and this was pitch black, it was midnight, you would not be able to see another human being. But if you got night vision goggles, what they do is allow you to detect light given off in the infrared part of the spectrum. So we are all giving off infrared light, and we're giving off more infrared light than our surroundings because we are warmer than room temperature. We're, what, 37 degrees Celsius. Room temperature is more like, I don't know, 21, 22. I like it cooler, so 21. So if you're able to look at somebody, you can actually pick them out because they are glowing. Just not a wavelength of light that we can see with our eyes. Get things hotter though, and like you can see this rock. I mean, this dark rock is still very hot, but not hot enough to really emit much, if any, visible light. But of course, when you get to the hotter parts, like down here, you see a lot of sort of orangish red light. And the first light that you're going to see is on the orange-red side. You have to get it hotter than that to get it into the white part of the spectrum. And if it's blue, it's going to be extremely hot. Okay, you're going to get on the much, much hotter part there as well. So yeah, you can see this too on the, I call these old-fashioned now, because it's hard to find stoves that have these old burners on them. My stove has them because when I bought it, my brother's wife's father, I'm not going to figure out what that means, was a appliance repair person for Sears, and he warned me against the glass top stoves because apparently, like, very common, someone will drop something and shatter the whole surface, and then you got to just pay $1,000 and have it replaced. Nothing wrong with these. They work great. Yeah, so they do well. So yeah, Yoda said, luminous beings are we. And he's right. We are giving off light all the time, just not visible light. It's all infrared. For an object at body temperature, what most blackbody radiation is emitted in, I don't know what I was,
You're doing so good with grammar right now.
yeah, I still have to, I got to reread these before I put them up. But you know what I mean. What range of light is given off mostly by some object that's at body temperature, 37 degrees Celsius? Infrared light is the solution to that one. You can see this is bats flying. They're warm-blooded as well. Okay, so we have this balance then of the Earth because it's warm, emitting energy all the time in the form of infrared light, which goes out and leaves the planet. That's offset by light that's constantly being absorbed by the sun. What we find is there's something that our atmosphere creates, which is called the greenhouse effect, where visible light can very easily penetrate through our atmosphere. It's transparent. It's kind of like glass, like the glass roof and walls of a greenhouse, where visible light, yeah, there's no trouble. It can go straight through that glass and be absorbed by some object inside. Once it's absorbed, it causes the surface temperature of the Earth to increase. That warms the surface, and then the surface will then re-emit some of that energy back out as infrared light. Problem is that infrared light has a hard time getting through, in this case, the glass, but in our Earth, it may have a hard time getting through the atmosphere. In fact, it can get reabsorbed by gases in the atmosphere, which then get warm and then re-emit light themselves. And they can re-emit the light back down to the surface of the planet. So kind of what happens is visible light comes down, gets absorbed, comes back out as infrared, gets absorbed here, goes back down is infrared, gets absorbed here, goes back up is infrared, and it kind of bounces, if you want, back and forth. Basically what's happening is the atmosphere is capturing some of the IR light the Earth is emitting, absorbing it and sending it back down. So it's preventing, or it's slowing down the amount of energy that's being lost from the surface of the planet. And this is actually a really good thing. If we didn't have an atmosphere doing this for us, or we had an atmosphere composed strictly of gases that cannot absorb infrared light, which we'll talk about later, the Earth on average would be about 20 degrees colder than it is now on the surface. So that would mean that Nova Scotia would be below zero almost all the time. Sure, we might get a month or two in the summer where it's on average warmer than plus 20, but we would lose a lot of the in-between months as well. So this is really good. This gives us a lot of, makes our life much more visible than it might be otherwise. All right. So CO2 is the one we always hear about, right? CO2 is the, and correctly, this is the number one most important greenhouse gas. So what's going on with CO2? We know CO2, there's a number of ways we can draw the structure. It has, we can draw like that, like that. It's got a carbon in the middle, 2 oxygens on either side, and there's a double bond between the oxygen and the carbon. What happens when you have any molecule that has these bonds? These are covalent bonds that we talked about in a previous lecture. When you have covalent bonds, is these bonds can stretch and compress. They can vibrate back and forth. So here we have a carbon in the center, we have an oxygen here and an oxygen here. You can almost think of those atoms as being kind of like hard balls, which are connected to each other by these flexible springs that can either be scrunched together or spread out, and they can kind of vibrate back and forth. Furthermore, to that, when you have a molecule with multiple, like more than one bond holding multiple atoms together, like you have in CO2, you can say there's one here and a second one here. Those vibrations aren't independent events. They're actually coupled to each other. So what we get are only certain types of vibrations which are possible, can possibly exist for a molecule like CO2, which may not make sense if you kind of think about it on the surface, but it's one of those very nice features of quantum mechanics that doesn't make a whole lot of sense in our everyday lives, but is an actual reality that we have observed and have seen. So basically what this is showing, this picture here is trying to show one of these possible vibrational modes is what we call them. One way that this molecule can actually vibrate. Where if you think about the carbon in the center as remaining stationary, and then you're stretching the two oxygens out together and then pushing them back in together. And they're kind of breathing in and out and in and out and in and out. That process is what we would call a symmetric stretch. So they're stretching, they're increasing at the same time as each other, they're compressing at the same time as each other. In, out, in, out, in, out. This is trying to show you another possibility, which we call asymmetric stretch. A-S-Y-M-M. This one is the symmetric. T-R-I-C. I have terrible handwriting. The symmetric stretch has this bond compressing while this second bond is stretching. So it's almost like the carbon, if the carbon's in the center, I'm going to try to, camera's backwards, so everything's working backwards. It's almost like if the carbon's in the center, the rest of it is kind of going back and forth. So we have compression on one side, expansion on the other, and it kind of vibrates back and forth that way. There's a few other ones that you see here as well. These two are the most important ones for sure. So what does this mean? These vibrations are associated, like there's different energy differences between these different vibrations. So if a molecule is vibrating one way, what you can do is if it absorbs infrared light, it can switch to vibrate a different way. So this is what the infrared energy can do when it's absorbed by a molecule. Infrared energy is not very strong. It's much weaker than visible, which is again much weaker than ultraviolet light. We saw with ultraviolet light that that's high energy. It can be absorbed by molecules and it can break bonds. Infrared light's too weak. It can't break bonds. All it can do is make it vibrate in different ways. It can excite the molecule into these different vibrational modes. Okay, so infrared light is low energy. It's associated with vibrational motion of these bonds oscillating all the time. There we go. Ultraviolet can break bonds. Infrared light causes the oscillations. Microwaves, actually, microwaves which are in microwave ovens are actually extremely low energy, way lower than infrared lights. It causes molecules to rotate. It doesn't even have enough energy to make molecules vibrate. But it can make them rotate, and that's actually what happens in a microwave oven, is it gives off energy that water can absorb. Water kind of rotates and then slows down, gives off that energy as heat, so it slowly warms up your food that way. So it's microwaves. Microwaves too, by the way, are like the energy range of light that's used in like cell phone towers, communications, things like that. So yeah, it's passing through us all the time. Maybe a little bit gets absorbed, but like you need a lot in order to generate enough heat to change the temperature of your body any significant amount. All right, so we know then that this infrared light that we believe is being absorbed by molecules in the atmosphere, like CO2, and then being emitted back, is associated with these vibrations that we know molecules with bonds can do. But there's a caveat here, and this is probably the most complex concept that we're going to be looking at in the entire course. It's the idea of putting together the vibrations with the idea of something called polar bonds, which is necessary in order for a substance to be able to absorb infrared light. Okay, so before we get into that very far, we have to explain what a polar bond is, which if you've done chemistry in, say, first year or organic or something like that, you would have seen this. But basically, we define a chemical bond as being two atoms that are sharing one or more pairs of electrons. So we have something like HF, where this line here is a chemical bond. We could draw it instead like this, where we take out that bond and replace it with two dots, those dots being the pair of electrons being shared. It's the definition of a covalent bond, sharing of a pair of electrons. What often happens if you have two different atoms that are sharing a pair of electrons, very often one of them has a much higher attraction for the electron pair than the other one does. In other words, they're kind of unequal partners. And the visual I often like to give here is you can imagine if there's two people lying next to each other in a bed, and you cover them in a blanket. Sometimes in this situation, when you wake up the next morning, one person has pulled the blankets onto themselves and they're all nice and cozy, wrapped up in the blankets, and the other person is shivering cold because the other person was a bit of a blanket hog. You can kind of think of this as like the two people lying next to each other in bed, and that pair of electrons is being like the blanket that they're both sharing. In this example, what's happening is the fluorine has a property called electronegativity, which is much higher than that of hydrogen, meaning it attracts that electron pair in the bond a lot more than the hydrogen does. It kind of wants to steal that electron pair. It's kind of like the blanket hog. It wants to bring it towards itself, wrap itself in those additional electrons, and bask in all that electron-y goodness. As a result, because electrons have a negative charge, the fluorine develops a negative charge and the hydrogen develops a positive charge. Not a full negative charge, so we give it this little delta symbol. The delta symbol means sort of partial. So this gets a partial negative charge, the hydrogen a partial positive charge. Because the fluorine is more electronegative, it wants the electrons to be closer to itself. And that creates this imbalance where one side has a positive, one side has a negative, and so we would say this bond now is polar. Polar means it kind of has a negative end and a positive end. We sometimes draw it with one of these arrows, which just shows the direction of the dipole and has this little plus sign on the back. So that's the positive end of the dipole. So many bonds, in fact, almost every bond that forms between two different atoms will be polarized either towards one atom or the other. It'll be whichever one is more electronegative will have more of the electron pair around it. It'll develop a partial negative charge. So every element in the periodic table pretty well has an electronegativity measured for it, and you can see it in this chart. The highest of all of them is found at the top right-hand corner is fluorine. Fluorine has the highest electronegativity out of any atom. It's a big electron hog. If you bond it to anything, it's going to steal as much electrons as it can, pull it towards itself, and leave whatever it's bonded to partially positively charged. Oxygen is number 2, and as you step away from fluorine, the electronegativity gets less and less. Notice that carbon is much different from oxygen, 2.5 and 3.5, meaning oxygen is a lot higher in electronegativity than carbon. So if you have a molecule like carbon dioxide, what happens is the oxygen will be pulling the electrons away from the carbon. So you have this partial negative on both of the oxygens and a partial positive on the carbon in the center. Okay, this is all a function of this electronegativity, which won, well, Linus Pauling I talked about before. He won 2 Nobel Prizes. Electronegativity was, is something he discovered, but that's not why he got a Nobel Prize. He got it for something else called valence bond theory, which we look at in first year chem. And he got the other one for the experiments on the radioactive teeth. That was the Peace Prize he got. So CO2, we expect to have these polar bonds, these dipoles maybe that look like this, which are there because those two atoms that are covalently bonded together have different electronegativities. Looks like they made a US stamp in 2008 for Linus Pauling. I don't know why the 41 cents is crossed out. But he just passed away 1994. My father-in-law heard him speak before. One thing about Linus Pauling is he was a great speaker and a great scientist. But he developed a kind of a weird theory towards the end of his life, which he spent, he had a big megaphone. Everyone wanted to hear him speak because he had 2 Nobel Prizes. But he developed this theory that like mega dosing on vitamin C can have all these health benefits, which is not true, at least according to my cursory understanding of nutrition. If there's any nutrition or dietitian students that can weigh in, please feel free. But I think mega dosing on vitamin C is bad for you, hard on your kidneys, etc. But anyway, my father-in-law went to see him speak, and that's all he talked about was this vitamin C stuff. So these were his 2 Nobel Prizes, 54 and 62. Question: oxygen is much more electronegative than hydrogen, which causes the OH bonds in water to be polar. What do we mean when we say oxygen is more electronegative? Oxygen contains more protons. Oxygen contains more electrons. No, it means the oxygen atom attracts the electrons in the covalent bonds more strongly than hydrogen, causing the oxygen to have a negative charge or partial negative charge, and the hydrogen to have a partial positive charge. Great. It works out for CO2. It has these 2 polar bonds, which are represented by these 2 dipoles. Because of the shape of the molecule, though, these perfectly cancel each other out. So overall, carbon dioxide, we would say, has no net dipole. It's not a polar molecule. It has no uneven distribution because these perfectly cancel each other out, making this a nonpolar molecule. That affects its physical properties. It means it's likely to be a gas at room temperature, which it is. Very common for small molecules that are nonpolar, like oxygen, like nitrogen, like the noble gases, like methane, like many, many other gases as well. But remember, we said we were going to put this idea together of polar bonds together with the vibrations that these molecules can do. And what happens with CO2 during its symmetric stretch? That just means, remember, the 2 oxygens stretch out, come back in, stretch out, come back in. At all points from when it's compressed and when it's stretched, the dipoles always perfectly cancel out, and it's always nonpolar. However, the asymmetric stretch has, at one point in that vibration, a short CO bond and a long CO bond, and at that fraction of time that it's in that sort of convoluted stretched state, it is polar. So what happens because of this asymmetric stretch is CO2 goes from nonpolar to polar in one direction to polar in the other direction and back. It vibrates back and forth, oscillating its polarity back and forth. And this oscillation is extremely fast. It takes place on the scale of, about 100 femtoseconds, which is about 10 to the minus 13 seconds. Very, very fast, these vibrations back and forth. But, because of this vibration, when it's vibrating in this particular way, it's going from polar to nonpolar to polar in the other direction. On average, they all balance out to nonpolar, but at a point in time, it kind of is oscillating up and down like a sine wave. So what happens is if you have a molecule that has a vibration where the polarity is changing, that can absorb infrared light because it can go from a mode that goes from nonpolar to polar and back again. Molecules that have this feature, that have bonds that change polarity as they vibrate, these can interact with infrared light, and molecules that have this feature can absorb infrared light. So this is the most difficult concept, or conceptually most difficult concept in the course, is putting together this idea of vibrations together with the idea of polarity and recognizing that, you know, as a molecule is in this asymmetric stretch back and forth, that the polarity is vibrating back and forth. It actually vibrates. Remember we said that light was a wave as well? It's when the light wave frequency exactly matches the vibration frequency that absorption can happen. So it absorbs light, that causes this molecule to vibrate in this way. It'll vibrate that way for a while and then emit the energy back, which goes back down to Earth. So that's why CO2 can absorb infrared light, because it has this stretching mode available to it. Not every molecule can do this. In fact, molecules like oxygen can't, because oxygen is just OO, nonpolar. If you stretch it, it's still nonpolar. If you compress it, it's still nonpolar. It never has a stretching possibility that turns oxygen into a polar molecule. Same for nitrogen, right? Nitrogen, yeah, you can stretch it out, you can vibrate it, but it's still nonpolar because the two atoms are always the same. You'll never have a polar bond. So oxygen is not a greenhouse gas. Nitrogen is not a greenhouse gas for the exact same reason as oxygen, which is great because these are the number 1 and number 2 most abundant gases in our atmosphere. Number 3, if you remember, is argon. Argon is like helium, single atoms. It has no bonds at all. So these things can't even vibrate. And if they can't vibrate, they can't absorb infrared light either. So the top 3 gases that are in our atmosphere, oxygen, nitrogen, argon, none of those are capable of absorbing infrared light, which is fantastic because most of the energy the Earth is emitting goes up through the atmosphere and out into space. Perfect. Remember number 4 though. Number 4 is CO2. CO2 is in our atmosphere. It does have that asymmetric stretch possible that causes carbon dioxide. It gives it the ability to absorb infrared light. And it only absorbs infrared light in a certain window, which is this part of the infrared spectrum. Wavelengths going from, I don't know what that is, like, I don't know, 13 to, 17 microns in wavelength. Water will absorb some. There's a window where nothing absorbs. Ozone will absorb a little bit up in the stratosphere. We need the ozone though. There's other gases, methane. That should not be N4O, N2O. Water will absorb a little bit more out there. So in this infrared light that's being emitted now by the Earth, CO2 is kind of in this sweet spot to absorb that energy, send some of that energy back to Earth. It doesn't absorb all of it. Some of it goes through, but it absorbs enough to cause some of that energy to come back to the surface of the planet. Next question, why are pure noble gases such as helium and argon not greenhouse gases? A, they only form polar bonds. B, they have no bonds and thus cannot have vibrations. C, they only form nonpolar bonds. And D, they are not present in our atmosphere to any significant extent. Well, the answer is B, they have no bonds, so they can't have bond vibrations, and therefore they can't absorb infrared light. It's definitely not D because we know argon is present in large amounts. It's like 1% of our atmosphere. So there's a lot of argon. If it could absorb infrared light, we'd have way higher surface temperatures here on Earth than we do have. It's kind of funny how everything about our planet is like kind of perfectly aligned to allow life to happen. The fact that the three most dominant gases all allow the temperature on the Earth to remain nice and habitable, and that corresponds to the temperature window in which water, which is the dominant liquid on the surface of our planet, stays in the liquid state, not so hot that it evaporates into a gas easily, not so cold that the dominant form is ice, as well as we have oxygen to breathe. You know, everything kind of about it is just kind of perfectly calibrated, if you know what I mean. But that's where we're left. I think this is where I want to leave it. We're 3:46. We're soon out of time. We went a little bit longer than maybe we should have, but I didn't want to leave that piece half done. I wanted to make sure we addressed the entire concept there of my brain's starting to fail me. That's when I know I have to leave. Entire concept of vibration, polarity, what is physically happening in a molecule and what characteristic it needs to have in order to absorb infrared light and therefore act as a greenhouse gas. Great. Thank you, everybody. Thanks to those especially who are here in person, and thanks to especially everybody who's here online as well, and anybody who's going to be watching this later. Hope you enjoy. Great. Check out the stuff that I put online, new. Make sure you get these questions done, and make sure you finish the previous unit's assignment questions before Thursday's class. Thank you. See you, everyone.